I presented this now 2 weeks ago for my PhD defense, so I'm a very recent graduate. And this is kind of a condensed version of my defense. So sorry for those who attended. So I will skip the kind of usual spiel and academia stuff, but you know that GPUs now, they're used pretty much everywhere. Vision, HPC, machine learning, all that stuff. And there's a reason they're so used. It's because they're a huge compromise between programmability, affordability, and raw performance. So it's kind of an obvious choice for many applications. So yeah, I mentioned that HPC, machine learning, and also more embedded applications for all the reasons I presented. The way you usually write programs for them, so you have more of the low-level stuff, so CUDA, HIP, maybe OpenCL. And if you're really a nerd, you can go down to assembly. So for example, AMD ships some machine learning applications which are fine-tuned, I guess, handwritten assembly. And if you're not really into that, you can also write more high-level stuff. So using Cycle, OpenMP, which has an offload to device function, OpenACC, and all that stuff. The issue remains that it's hard to diagnose performance issues on GPUs for a number of reasons, and mostly because, well, they're complicated machines. So they were usually designed for parallel graphics tasks, hence the name, but you can use them for pretty much anything now. And they draw most of their processing power from like parallelism, of course. So that's multiprocessing, so you have multiple processing units. Compute units, I don't know what's the NVIDIA name for it. Multi-threading, so on those compute units, you have multiple threads. And when they're executing those threads, you have instruction level parallelism, so pipelining and all the stuff. The memory subsystem is also optimized to improve bandwidth and to work with this high level of parallelism. Of course, all those reasons they're faster are also all the more reasons you can shoot yourself in the foot, because if you're not making use of, well, proper use of them, then it will be slow, well, at least slower than it could be. So this is an example. This is the CDNA1, so MI100 from AMD. It's pretty much the same thing for NVIDIA. And so you have shader engines. They all share L2 cache here and here. And in each shader engine, you have compute units. I think there's 40 of them. No. Yeah, I don't remember exactly how many of them, but this is akin to like, well, I guess a CPU core. And inside all of them, you have an L1 cache. Well, it's hidden. We don't know it's there. We don't have really data for it, but it's there. And of course, you have also the, I guess, memory inside the device, which all share, and also some local memory, but this is kind of irrelevant. So the way you usually profile your application will get performance data. The easiest one is using the vendor-provided applications, so that's NVIDIA Inside, AMD RockProf, Intel VTune, and you get performance counters, how slow you are, like how long did the kernel take, how many cache faults, how many, well, classic performance counter stuff. Of course, this is just sampling, well, not sampling, but this is profiling, so it's statistical, it's aggregated. You don't have any super precise information. You do have species sampling most of the time, but again, it's sampling, so if you have some niche issue, you can't really catch them. But I'm preaching to the choir here. I know you all use tracing. So there are a few, well, academia ideas about instrumentation and tracing for GPU kernels, but pretty much all of them that I know of have pretty bad performance. So they don't really care about how they're getting the data. They're mostly interested in getting data from how it's executed and then analyzing it, so you feed it into a performance model. And so one of the papers, for example, has kernel runtime overhead up to 150 times the original runtime. So that's I mean, that's pretty bad. So this is the basis for all my work. So there is no like efficient tracing method for GPU kernels. So I have 3 articles, each having an idea of how to reduce overhead. So the first one is, well, we know we can't do efficient tracing because of the super high level of parallelism on GPUs. And so if you wanted to do tracing the usual way, so in a shared buffer and writing events, you're going to have a lot of cache faults because you're accessing the same memory, etc. So if we avoid allocation of memory at runtime, then we can just write the events. We can reduce the overhead. So the idea is that you run the kernel twice. You count how many events you would have to write if you were actually tracing. You allocate buffers of the exact size, and then you rerun the kernel on the same input data, and then you have a buffer that you have for yourself, and you can't interact with them, so there's no atomic operations, any interaction with other event producers. And so that's the basic idea. You write it, count, allocate, and then actually trace in a private buffer. So it's implemented so we're running on AMD GPUs. It's an instrumentation pass based on LLVM IR, so intermediate representation. We have the first instrumentation which adds control flow counters. We also have instrumentation for the host, which saves the input arguments. And then we have the second instrumentation phase for the kernel where you write the events. So that's what LTGNG does. We can also keep the original kernel if you want to get timing data, but that's something you can get through RockProp, for example. The one caveat with this approach is that you assume deterministic execution of the kernel. So if for some reason your kernel is doing something else on the second run, for example, atomic operations would end up with a different result or a different order of execution, you may not have the same results. So the article is public. It's published on the ACM transaction and parallel computing. This is a small a representation of how you access the buffers. So if I'm thread writer number 0, I will just access, on the second run, I will access the offsets array at offset 0. So I know I can begin writing here. And I know that all of this is reserved for me, whereas the second one, or I guess thread 1, will access this. And we won't interact with each other, so we don't have to ensure concurrency. So we tried this approach on the Rodinia benchmark, which is a benchmark composed of many GPU kernels, and we achieve a much lower overhead over the kernel execution. So you can see the median overhead for the tracing instrumentation is about 1.3 times the original time, which is usually much lower than 150. We do see, however, a correlation between kernel complexity and the overhead we observe after that. But the general idea is that it works. It works well better than the others. If we think about how we could improve that, so the instrumentation phase is rather heavy because it's done in IR. And the way the compiler transforms the IR into actual machine code is pretty complicated, and you can't really write efficient IR if you're writing it for the end architecture. So a way to do that more efficiently would be writing instrumentation directly inside the backend or as a, binary instrumentation tool rather than IR. And of course, we're limited to kernels which have a deterministic control flow, which is a rather small subset of all possible kernels for GPUs. The way I worked around that on the first article was just well, guess, okay, if we allocate twice as much memory for each event, then you can, well, try and assume that you won't write on someone else. But again, it's not really deterministic. So which brings us to the second article, which actually tries to propose tracing scheme for performance analysis of computer kernels on GPUs. So we know that the first approach works, but it's not the best because it doesn't apply to all kernels. Also, saving context is kind of a pain because memory is most of the time constrained on GPUs, and if you're having your buffers twice in memory, it can cause problems. So what if we try to actually trace on the GPU as the threads are running? So we've developed, we presented 4 data structures to try and see how we could improve that. And the 2 axes we're focused on is memory locality. So try and not have all the threads accessing one single variable, so where we're at in the buffer at the current time. And also allocation granularity, so how often we're accessing the buffer and the shared variable saying, hey, I need to save space to write an event. So this is an example of how it works. All the work I've done works on so wavefront tracing. So a GPU is kind of like a very large vector processor. So you have a thread is actually a single lane in an SIMT processor, but we're working on the scalar unit. So if we only have the threads working, everything will happen on the GPU at the same time. And so we can only instrument in the scalar unit instead of the every single lane, which already saves time. So the first approach is a single shot buffer in global device memory. This is kind of a stupid way to do it. So you have a single buffer. Every time you write an event, you do an algebraic operation, incrementing a counter or the current pointer. And the value before you incremented that, you know it's yours, so you can write an event there. Of course, since every thread will access that variable, the performance will not be that good. Which is why we worked on the second one. We have a shared buffer, but there's one for every compute unit. The idea is that there will be, you won't have to share that specific pointer on the same cache line everywhere on the GPU, which should improve performance. The third data structure is just a global buffer, but you allocate chunks of a fixed size. So it's kind of like the original, the first version, but this time you allocate as you go instead of allocating ahead. And the last one, so the fourth one, is you have a buffer per compute unit and you allocate on that. It's all implemented by hand, GPU assembly. It wasn't, well, it was fun, not that fun.
Does the toolchain allow you to index per compute unit?
Sorry?
Does the toolchain, so the compiler, does it allow you from HIP level to index per compute unit?
No, that's why you have to do it using assembly. I'll get to that at the end. So this is kind of a visual representation of how it works. This is your ring buffer. Each time you atomically increment point occur, you know that it incremented by this, and then you can write here until here. And this is a representation of the allocation-based methods. So you increment by a larger amount, and then you can write in here, and then you allocate another later on. And the idea is that you don't have as many atomic operations as you go. So this is a small benchmark of performance, how long it takes to write an event. So as we can see, so here, green and red are the one atomic operation per event. So as you can see, there's much higher.
Can you see what are the axes? Because
okay, yeah, sure. So it's the number of concurrent wavefronts, so the concurrent threads, if you will, and the time it takes to write an event. So
Is the x-axis logarithmic or?
It's log, yeah. So if we focus on this spot here, you can see that the atomic operations, one atomic operations per event is pretty bad in terms of performance, but it starts to separate as we go to, we increase the number of concurrent wavefronts. And the one which has increased locality, so one buffer per compute unit, is actually way more resistant to concurrency, whereas the other kind of shoots up, which proves that it's pretty bad for real applications, I would say. Whoop. And so the allocation-based approaches are much closer to the original performance of the first approach. The problem with this benchmark is that we assume that we write a very large amount of events, and the way we get this time is by dividing the total time by the number of events. And that's not really what happens in real life, because here we assume that the buffers are completely full when we write them. Whereas in an actual kernel, what will happen is that usually you have way more threads than you have number of basic block executed in one thread. So we will allocate a large buffer, but we won't write it completely, so it won't amortize as good as here. But in this kind of a specific example, it's pretty close to the performance of the original method, which is pretty cool. This is the median overhead on the HEC benchmark, so it's kind of a larger set of kernels than Rodinia. And we see that we have pretty good overhead, even with so global mem is the one where we have one single buffer and we increment it atomically. It's higher, especially the mean, so there's a lot of outliers, especially the kernels which have a very large number of threads and a large number of events, so those will be the less efficient. But the allocation-based methods are pretty good in terms of performance. So allocation performs the best. We talk about also in the article about the optimal size for a buffer. It's about a page, not surprising. We also provide typical use cases for each method. And the problem that is shared among all those methods is that the traces are super large. So this is the thing we try to tackle in the third article, which is called Efficient Instrumentation and Trace Point Insertion for GPU Compute Kernels.
So can I ask
Yes,
a question?
sure.
So when you say allocation, you cannot allocate memory right on
No,
GPU.
so it's statically allocated,
Okay.
and then you say this spot is mine. Yeah, yeah. But this is what, so you can actually dynamically allocate on the GPU, but it's what's done under the hood. So you can use malloc inside a kernel.
Yeah, but how it is implemented is just the static piece. Yeah, exactly.
Yeah. So just by looking at a trace, the intuition behind this last part of the thesis was that the way a GPU works, so if you have, say, an if and then an else, and maybe half the threads, so the 32 threads here will go to the if, and the 32 others will go to the else. The GPU has to execute both if and else branches. So the first time you have all those threads which are active, and those ones are not doing anything. And then you revert the execution mask to what it was before, and then you you mask it to the other half, and then you do the else. So if you know how many threads you have at the beginning and how many threads went to the if, then you can actually compute how many threads went to the else after the fact. So the way we write that in a complicated manner is that if you know n-1 branches, you can guess the last one, which is pretty nice for a single if-else. It's not as efficient for switch statements, but they're not really common for GPU computing. And then you can compute the number of the actual execution mask as you go, because the execution mask entering a certain basic block is equal to the execution mask of all the outgoing edges of that basic block. So we process that using Kahn's algorithm, so it's topological sorting. So we know at any moment how many threads are active at one point, and we can guess how many threads are going out. It does not work for CFGs that do have a cycle, so we have to do DFS, find the back edges, and then you have to instrument those in all cases. So this is a simple example. You can see that, so for example, this is if, else, and then inside the if you have an additional if that doesn't have an else, so they both go to C. And so a simple explanation of what I've shown in the last slide is that if you know how many threads are active at A and how many threads went from A to B, then you know which threads did not go to B directly and went to C, which is kind of obvious, but we can compute that after. It's kind of long to analyze, unfortunately. Static analysis is pretty long, but there's a pretty stark reduction in the trace size, which is what we're trying to reduce. So on average, the number of events, I think, reduced by 37%, whereas the total trace size, because you have to write events, even though you're not storing the exact threads that are executing, reduces by about 25%, which is pretty cool. The issue is that it's not as efficient as we thought in terms of runtime overhead. So we see, so this graph is kind of a distribution of the runtime overhead. So on top, we have the original methods which trace up every basic block, and underneath in orange, you have the efficient version, which traces supposedly less. And it's not as stark as the reduction in trace size. So you can see, so the second one is the median. It's lower, but it's not 25% lower, unfortunately. Which leads us to think that there should be a more efficient way to implement that. And also the tracing, like actual instrumentation, isn't as efficient as it should be. So this is kind of a limitations and future work summary. So currently the instrumentation on IR is really not the most efficient thing, but we're kind of limited by how the compiler actually translates code and IR to the underlying GPU architecture and ISA. And that's not something we can do efficiently right now because there's no binary instrumentation tool for GPUs that are really working at that point. I mean, I know Dynance is trying to instrument AMD GPUs. There's also an AMD tool that they're currently working on, but it's not fully working now. The issue too is that GPUs do not allow you to synchronize outside of kernel bounds. Well, actually, they can, but there's no guarantee in terms of memory model that you can access data on the GPU as the kernel is running. So you have to wait for the kernel to be complete, and then get the tracing buffer back to the RAM and then to disk eventually. There's the fine-grained synchronization memory, which is actually PCIe Atomix, but of course it's pretty bad in terms of performance. So we could think about a way to synchronize between the kernel and the device and the CPU as the kernel is running, but that would take a bit more time. And also traces are large and difficult to represent to the end user and to process too. Lastly, we could also explore emergent architectures. So the MI300A, for example, has shared memory between the CPU and the GPU, which we could exploit to get tracing data as the kernel is running. I have a few more slides to kind of present trade-offs in GPU tracing, but that could be a bit more, a bit too specific if you don't have any background in terms of GPU. So yeah.
So if I understand correctly, you rely on the fact that typically GPU kernels run for a relatively short time.
Yes.
And whatever you allocate and write needs to be completely allocated on the GPU memory, and then it's only collected when the execution completes. So if you have a GPU kernel that would somehow run for a very, very, very long time, that approach would be a problem.
Well, it would be like the flight recorder mode on LTTNG, so you do overwrite.
Yeah, you could at the end, but not the entire execution trace.
Yeah.
So you don't have kind of the trace stream collection.
So you can do that. You can implement that. Implementing it efficiently, I don't think is really doable. So you can do, for example, printf on the GPU, and it's horrendous in terms of performance. But there's a way to actually send data from the GPU to the CPU as it's running. So you could theoretically do that, but the time it takes to flush the buffer to CPU would be, I think, way too long.
I mean, if you don't do that every event.
Yeah. That depends on the size of your buffer, I guess. Yeah.
So are you using shared local memory or managed memory, or what was it?
So it's not matched memory. It's the so it's bin memory.
No. So the SLM or whatever, like the managed cache, the managed H2 or whatever. No.
Yeah. Any more questions so far? Yeah, sure.
Yeah, in the previous presentations, you mentioned the future works in relation to data structures.
Yes.
Or to the online tracing. Can you elaborate on that?
Yeah. So currently, again, this is what Matthew was talking about. You cannot flush the buffer as it's running because you don't have. I'm sorry, I don't think I got the question right. Is that what?
Just the part of the data structures.
Yeah.
Are you applying a proposition for a new data structure or?
No, it would be more about how to efficiently communicate with the host. So I think the allocation sub-buffer scheme works pretty well. It's how you can tell to the CPU that it can be flushed. That's the hard part. So the data structure itself doesn't really change at that point. Yeah.
So so as you write from the GPU, do the CPU necessarily have access to that memory, or are there situations?
So it's not defined. Yeah. Okay. So I know. So there's a instrumentation library for NVIDIA GPUs. It's CoopT, I think. Yeah. And they provide like a sort of queue to send from the GPU to the CPU if you wanted to do tracing, for example. And the way they do that is polling on the same memory location. So I guess for NVIDIA they can do it, but again it's busy waiting on a single variable, which is not.
Is that busy wait happening on the GPU side or?
So it's on both. So if the buffer is full, the GPU will be busy waiting for the flag saying that it's being empty. And apparently it works. So I guess for them it works. HIP does not it specifically says it does not allow you to get data. Well, it does not guarantee you to get like actual coherent data back from the GPU as the kernel is running, because you have to specifically flush the write buffer from the GPU to have the effect on the data, and that's not something that is done well as you go. You would have to do that by hand.
Out of curiosity, is there a way to let a kernel end its execution while preserving the data on the GPU side? So you could start it later.
Yes, that's what the debugger does.
So
you could do that.
Theoretically stop the GPU kernel, flush your buffers, and resume it after.
Yeah, that's something that could be done. Yeah, you can also trigger an interrupt from the GPU which would then wake up the host to allow you to get the data. Yeah, that's what the RockGDB does to get access to your registers and the data. So that's something that could be done. Yes.
And does that interrupt guarantee that the memory is in a?
I think it does, because as long as you get into the interrupt handler, you can do anything you want. So you can actually flush the write buffer. And I think it even does that automatically. So that's something to explore, yes. Yeah, I think that's it for the presentation. So again, it's very large traces, so there will be future work, I guess, focus on how you can process the traces and present them to the end users. We could also hope for better compiler support and also hardware support, so memory, coherency, and all that. Thank you for the Dorsal Lab and also our industrial partners for financial and technical support. And yeah, that's it for my presentation.
Okay.